Welcome to AI Frontiers, where we explore cutting-edge research reshaping artificial intelligence. Today, we're examining 14 groundbreaking papers from June 8, 2025, all from the computer science artificial intelligence category. These studies reveal revolutionary approaches where AI learns from failure, reasons across multiple data types, and makes ethical decisions under pressure. From virtual survival environments to architectural design studios, we'll discover how these advances solve real-world problems while ensuring AI remains trustworthy as it grows more powerful. Picture this scenario. It's 3 a.m. in a research laboratory, and an AI agent is failing spectacularly at solving a complex puzzle. The search trees it constructs collapse into digital dead ends, with algorithms hitting walls at every turn. Most conventional systems would discard this mess of failed attempts and restart from scratch. However, recent research reveals that buried within those failures lies the secret to revolutionary breakthroughs in artificial intelligence. What if failure isn't the opposite of learning, but rather its most valuable teacher? Today's journey takes us through virtual worlds where AI agents develop sophisticated survival strategies, into architectural studios where AI systems design buildings, and inside neural networks of systems that can see, hear, and understand the world much like humans do. We'll discover how researchers are teaching AI to be more human-like in its reasoning while ensuring it remains reliably artificial in its precision. Most importantly, we'll explore how these advances solve real problems affecting all of us, from making cities smarter to ensuring AI systems remain trustworthy. To understand today's research significance, let's explore the landscape of computer science artificial intelligence, or CS. AI as researchers call it. Think of CS. AI as the foundational bedrock of artificial intelligence research, much like geology forms the basis for understanding earthquakes and mountain formation. While other AI fields focus on specific applications like facial recognition or language translation, CS. AI develops the fundamental principles that make all AI possible. This field tackles the big questions. How can machines reason about complex problems like humans? How can they learn efficiently when data is scarce? These aren't theoretical curiosities but challenges determining whether AI systems can be trusted with increasingly important tasks. The first major research theme involves the evolution of search and planning algorithms. Imagine navigating through a vast, unfamiliar city without a map. Traditional AI systems need successful routes from other travelers to learn effective navigation strategies. But what if valuable lessons could be learned from every wrong turn, every dead end, every failed attempt? This is exactly what researchers are achieving with subgoal-guided learning approaches. The work by Tuero and colleagues demonstrates that AI systems can extract valuable information from failed search attempts, treating failure not as wasted effort but as a rich source of learning. This breakthrough has profound implications for situations where successful examples are rare or expensive to obtain. The second theme revolves around multimodal intelligence, the ability to process and reason about text, images, videos, and other data types simultaneously. Think of this like a symphony conductor who must coordinate violins, brass, percussion, and woodwinds into a harmonious whole. AI systems are increasingly expected to understand relationships between different types of information, not just process them separately. However, this creates new challenges around behavioral hallucination, where systems might generate plausible-sounding but inconsistent responses across different modalities. Coordinating these different information types harmoniously represents one of AI's most complex current challenges. Real-time decision-making represents the third major theme. In our increasingly connected world, AI systems cannot afford to take their time pondering decisions. Whether it's an autonomous vehicle deciding how to respond to an unexpected obstacle or an emergency response system prioritizing resources during a crisis, speed matters critically. The work by Jung and colleagues on rapid-reflex agents addresses this critical gap, developing systems that can make good decisions quickly when every millisecond counts. This research tackles the fundamental challenge of balancing decision quality with response time in high-stakes environments. Several groundbreaking results emerge from this collection of papers, each representing significant advances that could reshape artificial intelligence thinking. The first breakthrough fundamentally rethinks how AI systems learn from experience, showing that valuable information can be extracted from failed attempts rather than requiring only successful examples. The second major breakthrough involves developing AI systems that balance decision quality with response time through dual system architecture. A third significant finding relates to detecting and mitigating behavioral hallucination in multimodal AI systems. The fourth breakthrough demonstrates that general-purpose AI can be effectively adapted to specialized professional domains, with the BIM-GENT framework achieving 32% success in architectural modeling compared to 0% for baseline approaches. Now let's examine what I consider the paper of the day. DeepRL needs deep behavior analysis, exploring implicit planning by model-free agents in open-ended environments by Simmons Edler and colleagues. This research represents a methodological breakthrough challenging fundamental assumptions about how AI systems learn and plan. The central question strikes at artificial intelligence's heart. Can AI agents exhibit sophisticated, planning-like behavior without explicit memory modules or world models? The researchers created ForageWorld, an experimental platform capturing real-world decision-making complexity often missing from standard AI benchmarks. Picture a virtual ecosystem where AI agents must survive by finding food while avoiding predators and managing depleting resources. What makes this research truly innovative is their methodology borrowed from neuroscience and ethology to study AI agents like biological subjects. They analyzed movement patterns, resource utilization strategies, risk assessment behaviors, and temporal dynamics of neural representations. It's like having animal behaviorists studying artificial creatures, applying decades of biological research to understand artificial intelligence. The inspiration for ForageWorld came from observing the lead researcher's pet cat hunting behavior, noticing sophisticated strategies emerging from seemingly simple stimulus-response patterns. This personal connection between biological observation and artificial intelligence research represents the interdisciplinary thinking driving breakthrough discoveries. Their key finding challenges conventional wisdom about AI learning. Through detailed behavioral and neural analysis, they demonstrated that AI agents using simple recurrent neural networks can exhibit structured, planning-like behavior purely through emergent dynamics. The agents developed sophisticated foraging strategies, showed evidence of spatial memory and route planning, and adapted behavior based on environmental context suggesting internal world models, despite being trained with algorithms that supposedly don't build world models. The neural analysis revealed rich structure in learned representations, including evidence of place cells similar to those in animal brains, path integration mechanisms, and hierarchical temporal representations emerging naturally from the learning process. The broader implications extend far beyond reinforcement learning. If sophisticated planning can emerge from simple learning rules, it suggests that distinctions between different AI architectures may be less important than previously thought. This could lead to more efficient AI systems achieving complex behaviors through simpler, more robust mechanisms. The methodology they developed for analyzing AI behavior could become a standard field tool. Just as neuroscientists use multiple techniques to understand brain function, AI researchers may need more sophisticated analysis methods to understand what their systems actually learn. This represents field maturation, moving beyond simple performance metrics to deeper understanding of AI cognition. Looking toward the future, the research landscape painted by these 14 papers suggests we're entering a new phase of AI development. Think of it like the transition from early flight days, when inventors focused on simply getting off the ground, to modern aviation, where aircraft are designed for specific purposes while meeting safety and efficiency standards. AI is moving from proving it can work to ensuring it works well, safely, and in alignment with human values. The convergence of themes points toward AI systems that are more robust, interpretable, and capable of handling real-world deployment complexities. We're seeing AI emergence that can learn from failure, reason across multiple information types, make ethical decisions under time pressure, and adapt to specialized domains while remaining transparent. The human stories behind this research remind us that AI advancement isn't just about algorithms and data. It's about creative, dedicated people asking profound questions about intelligence, learning, and what it means to think. From researchers inspired by their pets' behavior to teams working to ensure AI systems remain trustworthy, the human element remains central to this technological revolution. The field is tackling AI safety and ethics head-on, not as afterthoughts but as fundamental design considerations. Every breakthrough begins with someone asking a question others thought impossible to answer, and today's research shows a mature field understanding the stakes involved in developing AI that serves humanity's best interests. Today's exploration reveals a field in dynamic transition, moving from narrow capability demonstrations toward broad, reliable, and ethical intelligence systems. These advances matter because they bring us closer to AI systems helping solve humanity's greatest challenges, from climate change to healthcare to education. The breakthroughs in learning from failure, multimodal reasoning, real-time decision-making, and specialized domain adaptation represent significant steps toward AI that can truly augment human capabilities. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from archived preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer. This video uses archived preprintserver.org content under its API terms of use. AI Frontiers is not affiliated with or endorsed by archived preprintserver.org.